everyone, I'm Macabeus. I'm speaking from Portugal, okay? And so let's start to talk about reverse engineer a Furry Gameboy Advance game. Probably you are a what the fuck about the subject, and I introduce right now. Well, there's an old and nostalgic game called Klonoa. I really love this game, and this game runs on Game Boy Advance. It was a very popular console of its time, so there is a lot of documentation and tools that help you to create a reverse engineer tool for this platform. So it's a good touch point to learn about this amazing subject. And here is a video display how is the Klonoa game, and you can notice that it's a very simple tile-based puzzle game. But this game there is a few couple of levels. I want to play more levels, and even more, I want to play my own levels. So let's write together a Cloud2Bjs, a reverse engineer tool to customize the levels for this game. You can check the GitHub repository with the entire source code, and at the end of this talk, I will do a live demo using that. And to this challenge, you will use two tools. The first one is NoCacheBA, and the second one is IDA. On the left side, you can see NoCacheBA running, and the right side, you can see IDA. NoCacheBA is a powerful tool to do dynamic analysis for this game, but it lacks features to do more powerful analysis, such as graph visualization for the assembly code, insert comments, and so on. So to cover these missing features, I use IDA. Okay, we want to develop a so complex project. There is a lot of things to do. So let's start simple. At this moment, I want just to stretch the bridge on this game because it's easy to customize something instead of create a new one from zero. So at this moment, I want just to stretch the bridge on the game and using NoCacheBA. Here is the bridge that you want to make it bigger, okay? And in NoCacheBA, there is a lot of panels to do analysis on the game that's running. And on this panel, you can check the background in the tiles. And here is the tile that you on the corner of the bridge. Each tile there is a specific ID, and the corner tile for the bridge, the tile ID is 9B. The continuous part is 9A. And you can see the memory address in which tile is stored. In this case, the tile is stored at 0600F18D. It's not a surprise that this tile is stored in this memory section because GBA that has a lot of memory section. For each section, there is a specific purpose, and this tile is stored at VDRAM that is useful to display on the screen background and the sprites. And okay, you can go to this address, and you can see your tiles of the bridge, nicely, and you can update this byte, this there on the memory to make it bigger. So it works, right? And running one frame on the game, yes, you can see your tiles, but on the next frame, extra tiles disappear. What's happening? Well, to understand what's happening, we need to understand the DMA. Doing a very simple test to walk to another part of the level, you can see that the entire time map changes on VGRAM. So we can notice that it will only store what the player has to see in the given moment from somewhere else that has the entire tile map. But where's the entire tile map stored to say the information VGRAM for each frame to update this memory section? Well, reading more about how the Game Boy Advance works, I found this amazing book. And in this book, in the chapter about the tile map, it introduces an important subject called direct memory access, in short, DMA. Well, it's a feature of computer systems that allows certain hardware subsystems to access main system memory independent of the CPU. In short, it provides a way to copy and paste faster. It makes sense because the visual is too small to store the entire tile map. Then it's necessary to store the entire tile map in another memory region and set a part of it to the visual. And using NoCacheBA, there is a feature that allows to track the DMA communication and run one frame on the game. You can see that it made 4 copies. And on this copy, on this result, this is closest to the byte of the bridge. In other words, visual is updated here by this DAA communication. And this is the address of the visual data source. So GBA replaces the visual with the data starting from this byte 0300 and this byte is located in another memory region called flash W. There's a large one. So instead of changing the byte at the visual, we need to change the bit byte at the flash W. And so going to this address, you can find the bit starts here. Very nice. And so you can update the styles to make the bit bigger, okay? And you run the game. Yes, it's working. It's not disappearing anymore. But you can see the extra tiles. It's not disappear anymore when you run 1, 2, 10 frames, but you can't stand on it. Why? Doing the very simple test, okay. Again, walk to another part of the level, we can notice that your extra tile disappear when out of the play visual range. So there is another memory region that will store the entire tile map and is the data source for both fast W and visual. But where is it? Where is it? So I don't really know where is the entire tile map. Neither a better way to find it. So I choose to understand better how the physics works on the game. Because if you understand how the physics works on the original tiles, we can copy this behavior to our tiles. But before understanding what attaches the Klonoas to the floor, we need to approach another important feature of GBA, the Object Attribute Memory, in short, OAM. Well, since the GBA is a hardware to play games, it has many features to work well with games. One of these is OAM. Each object or OAM looks like a tile, but you can move it, change its sprite, size, and use another panel from non-cache GBA. You can see the address which you know is stored in the memory, stored at this number. And read again the DAA logs on non-cache GBA. We can see exactly the byte that was on Klonoa's object. So the bytes from this address are the data source of the Klonoa's object. So we need to track the change on the byte 03004800. And doing this analysis, the first byte on a object defines the Y position. It's a common for every GBA games, okay? And you can update it to 12, for example. And see the display and run the next frame, you can notice that it changed the Klonoa's Y position, but it also returns this byte for the correct value. And so run the next frame, Klonoa continues to find should be not happening. So okay, we are on the correct path. We find the byte that defines the Y position for Klonoa, but we need to understand better details how the Y position is updated. And doing a lot of reverse engineering that I won't have time to explain in this talk, I found the important thing. We was look the byte that defines the Y position to the camera. And for example, on this image, you can notice that Klonoa's is the same Y position to the camera. So these bytes are the same, but it's not the same position in game. But close to the byte that defines the Y position to the camera, there is another byte that defines the in-game Y position. And so this position is not the same in-game, so these are different. And so we need to look how this in-game Y position is updated. And after a lot of research, I found that this block is where updates the in-game Y position. And in the upper block, decides if should or not update the Klonoa's Y position. And checking the detail of this block assembly, we can note that it uses the tile ID stored at the slow W and not fast W. And the slow W is another memory section. There's a large one, and the game stores the entire tile map in this memory section. And after update the tile map at the slow W, yeah, finally, you can create real tiles. It's not disappear anymore, even when out of the playfield range and you can stand on it. Very nice. But okay, very nice that you can create real tiles on the game. But we want to create a level editor that runs on the browser. So we need to find the tile map on the ROM to be able to extract it and deploy it on the browser. It's one of the most important reasons that one should have at this project. Why the information flow has this way from the cartridge to slow double run to the fast double run to visual and finally to display, we are walking on the reverse way. Use the clues that we find on the path to walk from display to slow double run. And because there isn't any memory region before slow double run, we need to use the tip to find where the tile map on the cartridge. So running the step-by-step debug to see the structure that writes the tile map at this loadable run, we found the level loader. And the level load is used the structure called the SWI. What does it mean? Well, let's talk about SWI structure. There is software interrupt. Another name is BIOS calls. Well, BIOS is a firmware that stands to install the physical components of the system. In GBA, it's by expose many functions, often used in games, including data compression and decompression. Each function has an associated numeric code, which must be used as a parameter in the SWI statement. So, for example, let's see how the division works on GBA. Its structure number is 6, so the assembly code should be SWI6. And we should write the parameters to the registers. The R0 is the numerator and R1 is the denominator. And the output of the divider will be stored on the registers, okay? It's the same case for every function called use SWI. And in this case, the software is called the Huffman decompress and LZ77 decompress functions. And the Huffman plus LZ77 is the same of the Flake, a very popular algorithm used in, for example, zip and PNG images. And to check the parameter on these instructions, you can find the address in which the complex the blob, okay, and going to use either choose address on the parameter, you can find the entire blob of the data level. Okay, and you can just need to push the cursor on the first byte, and either you highlight the entire blob. So it's very good. And you can use either to export it into a separated file. Okay, so now we have a file with the compressed data of a level. Then you need to uncompress it using the same algorithm, Huffman plus LZ77. Well, do you remember that I said at the beginning of this talk that Game Boy Advance is a very popular console and many people made awesome tools to work with it? So, a person made a few years ago an open source tool written using C with the same algorithm, compressor algorithm of the GBA. To use it, we just need to send the file path that it will uncompress it in place. And use it, you can notice that the tile map bytes on slow double run and from the uncompressed file are the same. So it's working well. Nice. Okay, we found the tile map on ROM and you have a file with this data. And since we want to build a level editor, now we need to paint this tile map to be able to edit it. But you have a new challenge. We have just a vector with the data, and you need to plot it as a bidimensional image. For example, all these plots are valid, but just one of these are they used on the game. So we need to find the correct one. Where is the new line? And you have an import flow to help us. The size of the buffer and the probability, the height and the width are natural numbers because it doesn't make sense a half tile. So we just need to find the height or the width and we find all the variables. You can find it doing a dynamic analysis on the game. Think with me. I am on tile A, and below me is the tile B. From the tile A to B, there are 9 bytes. In other words, 9 tiles. So the length of this tile map is exactly 9. We can reproduce the same idea on the game to find the length of the level. Firstly, we need to get the address of a tile, okay? And we need to set a breakpoint here. I found this structure while I was studying about how the physics works on the game. And in this moment, the R0 is the tile address in which Klonoa is stand on, okay? And you can go to this address to get the tile map data. And when I change this byte, it reflects right there. It's your tile A as this memory address. Then we should update the tiles below Klonoa to drop him one level. And you need to get the tile address one level below. Change this byte. We found the tile B, exactly at this memory address. And because we get the address of the tile A and B, we can subtract to get the length of the level. That is 420. And divide it, we find the entire size. With the entire size of the buffer, we get the height of the level. Now we can plot it, right? But before we develop the web application itself, it's very important to create a few simple proof of concept, just to validate our idea. And so I choose to paint the time map as the BMP image. And to do it, I am using the GIMP library. And here is the load the library and the tile map, okay? We should to drop the first 3 bytes of the tile map because just a header that I don't need to use right now. And so we need to paint with white if the type code is 00, otherwise paint with black. Then we need to do a loop on the tile map array to paint each pixel at the BMP image, okay? It's a very simple code just to validate the idea. And after that, yeah, you can see the tile map of the first level of the game. Nice. By the way, I notice that in all levels, there is this schema in the corner. It's not just a palette with the tiles available for this level. And to be sure that your process is really working, I will produce the same step-by-step on the sector level. And yes, it's working very well. And with a very boring process, you can map each tile ID to a color to paint a better image, okay? But use the same schema from the level 2 into the level 1, the result is not good. The green color is grass, but there is no grass on the top of the level. One gotcha is that each level has a different schema. And it makes sense because if our level had the same schema, the entire game could have just 255 different tiles. But the game needs more than it. Okay, let's see the project running. Okay. Here is the GitHub repository of this project, okay? And the click in this link, you can open the web application. Okay, the first thing we need to load a ROM file. Let's load this first ROM. Okay, it's the Gameboy Advance emulator running on the web application. You can load the first level, color division in game, okay? So load the first level. Here is a tile map of the first level, very nice. Automatically enter the first level. You can select other level, like the level 5, for example. There's a bigger level. And automatically enter in this level, okay? So let's go to the first level again. Well, there is this monster. I don't like this monster. So let's block it. Create new tiles here, okay? And let's get this another tile, okay? Then you should update the vision to see your chances, okay? Now you block the monster. I don't like this monster. And so you can update it to, let's see, I like it to be a star. A star is better, I like stars. And let's get this on the monster right there, okay? And so update the vision again. And okay, now we have a star in the beginning of the level. You can set some hacks like a infinite hat, infinite lives. It's very useful to test the more complicated game. So I don't lose any hat. You can set a show grid, hit grid, zone in, zone out. Okay, and these numbers is just a teleport to go to all the parts of the level. So you can set some tiles here to teleport to another part. And so teleport to another part of the level. Okay, very nice. But how this application was coded? There is one more thing to show. Browser file, open this other ROM data, and go to the first level, DEFCON fun. There is possible to do a lot of things on this application, just for fun, it's very nice. Okay, there is a lot of things on this application, but how I coded that? Okay, let's return to the presentation. Okay, open the slides again. Okay, coding. Let's talk about the stack. Well, I am using React because I love the declarative way of doing a user interface, and it provides a easy state management, okay? There is no backend for this application. It runs only on the browser, and its GitHub page is enough for that. And I am using WebAssembly, and I will explain why soon. Architecture. Well, despite the application is just a front end, I split it into two parts. The first part is colored brush, is the React application. It's my front end itself. And the second part, colored scissor, is a JS library to handle with the ROM. And so brush loads scissor, and they use it to extract the data from the ROM, get constant values, put the ROM data, and so on. WebAssembly, why I am using it? Well, I get the file map code from the ROM, and I am using a C code to uncompress it to get my decompressed tile map. But we have a problem. You can't run C code on browser. One solution would translate the C code into JS, but it would require a lot of work to rewrite it into JS. And another solution is compile the C code to WebAssembly using mscripting, and I picked this approach. mscripting generates both the WASM files and JS wrappers to make it easier to use. Okay, let's scroll into this code. The first thing is load the wrapper generated by mscripting. And on the original C code, like I said before, all the communication is based on the file system. But we don't have access to file system on the browser. No problem. An amazing feature from mscripting is emulated the file system. And so I didn't need to change so much the original C code because you can continue to use a file system in the C code that will be emulated in another file system. And so we move the buffer from ROM to a file in the emulated file system, okay? So we need to call the WebAssembly function to decode it, and after that, read again for the emulated file system, the buffer of the file. And the change is in place, and so we need to read for the same file. I also wrote a shell file to be easy to call the mscript compiler. I am using Docker. And we need to pass an additional compilation flag to include the emulated file system. And after that, we got the three-line function that reads the ROM data and they run the both decompressed algorithm in the same order that the game is calling, Huffman and the LC77. Okay, another part of this project is save the new tile map in the ROM. And there is some tricks to learn about that. Each level is stored continually at the memory. So there is the first level, and exactly in the next byte, there is the second level, and so on. And you can change the first level using CloudBGS, but the customized first level could be bigger than the original one. And if you try to save it in the original address, you could overwrite the beginning of the second level. And if you try to load the second level, it will crash. How to solve that? Before to show the solution, I need to explain in short a little more about how the ARM works. On ARM v7, the CPU used on GBA, there are two instruction sets, thumb and ARM. Most Game Boy Advance games are written using thumb because it's fast to run and demands less memory. The another instruction set called ARM can perform more complex instructions. And the switch between ARM and thumb must be done by BX instruction. And this instruction only can read a registers, and the current BX instruction update the program counter by the register value used in its parameter. Okay, now let's talk about the solution itself. If the cartridge is very small, there is a big hole space at the end of the memory. And it could be very useful because you can add some custom instructions in this section. And I will explain what I added right now. Well, the first thing is a table map the original address of the tile map and the address of the custom tile map. For example, the first line of this table is the original address for the first level, and the second line is the address for the custom first level, the same for the second level, and so on. And now we need to patch the instruction to load a level. We place the instruction to jump the program counter to your custom level loader. So we need to update the instructions, okay? And R0 is the point to which the tile map will be loaded. So we should update it to the address of the custom level loader. And that's how I did it in this another function. Well, first I need to switch from thumb to ARM because it'll be easier to write the custom level loader use ARM instruction set. And so I use this trick and move it to R0, the program counter, and add 3C in the R0, and so call BX use R0. And here is the logic to replace the value at R0 to the corresponding value from the table. And the first thing is just to original code from level loader to have the correct value at R0. And so you use this function walk on the table, check if it has the R0 value. If yes, replace the R0 with the corresponding value, like I said before, from the table. And just a code from the original level loader that was replaced to add the jump, and returns the level loader using thumb. And it's the idea to save a customized level on the ROM. The first thing is to redirect to the patched code, check if the R0 is on the table. If yes, load the associated value and return the original loader. And the result, what I got with that. After I launched the very first version of this application, even the very, very simple first version, I shared in some Discord channels to receive some feedbacks, seeing the players use it, because it's very nice to see my application being used. It's very, very good feeling. And the same minutes that I launched it in some Discord channels, this guy was using to draw some images. One guy was asking how could help me to improve that. And there's even a guy that make a very, very nice to play. And in this level, it's very hard to play because you need to use some speed run techniques to be able to pass. So it's very hard that I can't pass this level. It's like a Kaizo level for Klonoa. Other projects. Well, the emulator on CloudBGS, extract it in the separated package, okay? So if for some reason you want to have a GPA emulator on your web application, you can use this package, okay? It's a wrapper into GPGS. And we are. Well, I am Bruno Macabeus, a software engineer at OutSystems. Here is my GitHub. You can check all the projects that I'm developing. And follow me on Twitter to check some news for this application or the application that I like to develop. Thanks to Matheus Albuquerque that helped me to improve the front end and to prepare this presentation. Thanks to Raul that draw all the images, logo, icon. Thanks to Ray Carrot that helped me to extract the sprites from the ROM. This guy is developing Ray 1 map that's a level view for many, many games. And thanks to Matt that helped me to improve the emulator. This guy is developing Smagesh, that's a level editor for Super Mario Advance 4. And this talk. You can check the GitHub repository to check the entire source code. And in this README, there are the links for these blog posts. You can read the blog post in English, Portuguese, and Spanish. There's 10 chapters explain in very close details about how was the reverse engineering process. There's topics that I didn't have time to cover in this lecture. You can learn a lot with these blog posts. And in the README, there is also the links for the previous talks that I gave in some other conference. The first talk was in the conf, the biggest Brazilian international tech conference. And the second conference was in Balsicon, a security conference at Serbia. And thank you, obrigado. Yes, I am check the Discord channels if the channel about the questions. Okay. The real-time modification. Also, yes, okay, yes, very thank you. Yes, WebAssembly is a very good thing to use because I will demand a lot of time to rewrite the C code in JS. So use WebAssembly as a tool was a quick win. Yes, and I did make the emulator. Okay, I just wrote a wrapper over the GBJS. Okay, the GBJS is the same guy that makes the MGBA. It's a powerful GBA emulator. Thanks, Edric. Is there a published list of software used? Yes, Drake. I'll share my screen to be easy to show the questions. Okay. Okay. Uh, uh, just move the tab to another thing. Yes. Okay, so yeah, there is enough anything space on my Discord. So okay. Yes. Okay, Drake. Is there a published list of software used? Yes. I use it only no cache BA, and I need to use a virtual machine because I'm using Mac, and so I need and the no cache BA only can run on Windows, but okay, it's not special. And I use the either. The guy that is developing the RAID one map is this guy was not using either. He's using the NSA tool that I forgot the name. Grid, I forgot the name. But yes, either it's enough, and no cache base is enough to be able to do this project. Have you tried with other games? No, I'm focused only on Klonoa's game, okay, and the first GBA Klonoa's game. But the process would be replicated to the other games that is the same, okay. The way the again the rate one map is the map view for many games, so you can check this application to see how to generate a abstract architecture to use on the other games. Okay, the rate one map. You can check this project. It's very good to learn about how to develop a general map view for many games. Thanks, and thanks.